I just pulled the power cord on a massive server filled up with virtual machines and containers. The industry says this is a huge blast radius risk. But what is the actual impact? Let's talk about it. I want to tackle a massive debate in the industry. Does buying a monster server increase your blast radius? What are the recovery times for small versus large nodes in the same size clusters? How to prevent blast events or at least minimize its radius? I've built 2 OpenShift clusters, one in standard size, the other is double the size in every way. We're going to benchmark them, fill them with VMs and containers. I'm pushing all this with compute, storage, and network intensive tasks. And then we're going to break them. Let's look at the contestants. Small on the left, large on the right. 2 disks each for the operating systems. The heart of the node is the CPU. 64 total physical cores on the left and double 128 physical cores on the right. We're going with OpenShift Data Foundation for storage, and to get twice as much performance on a large cluster, we're doubling the amount of NVMe drives. Finally, the network, an active-active LACP bond on the left and quadruple active bond on the right. The secret here is balance. If you double the CPU cores but keep the network skinny, you create a bottlenecks. We scale the pipes to match the compute. We're building 3-node compact clusters on both sides to achieve the most impactful scenario for the blast radius. Each node down is a 33% impact to the workloads. That will teach us. Now the workloads. 60 high resource consumption VMs on a small cluster and double that amount on the right. Same for containers, and I think you might be able to see the pattern. For full transparency, the small cluster runs on modern Intel CPU, and my monster cluster is a 5th gen AMD EPYC CPU base, and I love this thing. But wait, this is not a bake-off, as both AMD and Intel have high core count SKUs in their portfolio. The full spec of the equipment used in the description down below. Before we break things, let's check the pipes. Here's the iPerf 3 for networking. As expected, cluster 2 is pushing roughly double the throughput. And here's the storage benchmark using Rados Bench. Because we doubled the NVMe drives on a big cluster, our IOPS are doubled as well. This is crucial. If the storage was slow, recovering our VMs would take forever. We confirmed our baseline. It is time to scale the workload. Ansible automation is your friend here, and I've put the playbooks used for this setup in the description below if you want to replicate this in your own environment. Scenario 1. Patch day. You need to drain a node. We're checking the load first. 60 to 70% compute utilization should be enough to leave enough room for our workload to evacuate. Also, the VMs seems to be spread equally across the cluster. I'm running a continuous ping to a VM inside each cluster to observe impact on the workload. I'm going to issue the drain command on both clusters simultaneously. Since my storage is hyperconverged, it is important to not evacuate the storage first. Otherwise, the results will be random. Watch the ping. We're looking for dropped packets. While this drains, notice that even though cluster 2 has doubled the data to move, it has doubled the amount of available horsepower to operate. Done. And what a surprise! The monster cluster took almost half the time to drain as the smaller one. Why? Because we didn't starve any of the resources. Double the size equals double the headroom on the recovery. Since we stressed CPU, memory, storage, and network on the VMs, we ended up dropping a few pings, but again, due to large pipes, the monster cluster handled it way better than the smaller one, and that workload just migrated. Yes, this is a plot twist. I have to admit that I didn't expect such a result. I had to run it a few more times to believe it, and even though the difference was not always that substantial, the large cluster consistently recovered quicker. Okay, playing nice is over. Now for the unplanned outage. I'm going to simulate a total node failure, reloading the workloads and getting them into balance first. The same total cluster utilization of 60 to 70%. I'm using Redfish to hard power off one node in each cluster. I hope I turn off the right one, otherwise the demo is over and I'm going to lunch. The nodes are down. Now we rely on SNR, self-node remediation. OpenShift detects the node is unhealthy. Watch the VM recovery. Since the pods and containers are controlled by deployment, they will just restart. But the VMs need to be rescheduled. There, cluster 1 is recovering, and look at cluster 2, it's right behind it. We just recovered all VMs on the big cluster in roughly the same time window as the small cluster. The blast radius was larger in terms of count, but the impact duration was almost identical. So we proved that big servers can recover just as fast if the I/O is there. But you still want to sleep better at night. How do we minimize the risk further? Number 1, intelligent remediation. We used SNR self-node remediation today, which is the easiest one to set up, but also the slowest to react. You could also use FAR, Fence Agent Remediation, which is faster and more reliable. I'd say this is highly recommended with virtualization to ensure quick recovery after an unplanned outage. If you're coming from a VMware world, this is similar to the VM high availability. Number 2, the descheduler. Don't let one node get too hot. We can run the OpenShift descheduler to constantly balance VMs based on CPU utilization. This prevents one node from holding 90% of your eggs. Again, for the VMware folks out there, this is an alternative to the DRS. Finally, number 3, distributed architecture. You know who are the largest providers of the compute infrastructure? Of course, it's public clouds. Minimizing a blast radius is one of the reasons why they break the monolithic architecture into availability zones and regions. And you can do that with OpenShift as well. In production, at least use a leaf-spine network topology. If you need to increase the number of nines in your SLAs and SLOs, split your OpenShift nodes on different racks and leaves and use an external HA load balancer. Even if a rack dies, your apps stay up. This is a topic for a separate video, and I have one for building a simplified version of that. Link in the description below. If you're still worried about putting one huge control plane on a massive server, there are 2 additional alternatives. Option A, hosted control planes. You can run multiple hosted control planes on this large bare metal cluster. This creates a logical separation. If one control plane has an issue, it doesn't take down the neighbors. Option B, inception model. Since we're automating everything with Ansible, you can deploy a massive bare metal cluster and then use Ansible to deploy smaller child OpenShift clusters inside VMs on top of that metal. This gives you the raw power of AMD EPYC cores, but the isolation of small clusters. It's the best of both worlds. Again, 2 huge topics that would require dedicated videos. Drop a comment if that's something you would want me to record. The summary is this: don't be afraid of density. The economics of modern CPUs are hard to beat. The fear of a blast radius is managed by architecture, better networking, faster storage, and smart remediation strategies. I'd still love to hear your horror stories though. Have you ever had a massive node failure that didn't recover? Let me know in the comments below. As always, I hope this video has been helpful, and thanks for watching.